name of Almighty God, I'm Master Sankoshi, and today I want to talk about plasma, focus-based repetitive source of fusion, neutrons, and hard X-rays. This was written by Rospa and his colleagues, and it is related to the department de Frica and in the Tandil, Argentina. The abstract is a plasma focus device capable of operating at zero point 0.2 pulses per second during several minutes, is used as a source of hard X-rays and fast neutrons. An experimental demonstration of the use of the neutrons emissions for radiation probing of hydrogenated substance is presented, showing a particular application in detecting water concentrations differences in the proximity of the device by elastic scattering. Moreover, the device produces ultra-short hard X-rays pulses useful for introspective image of small objects static or in a fast motion, suitable for the identification of internal submillimetric defects. Clear images of metallic objects shielded by several millimeters iron walls are shown. The background of this literature pulsed sources of fusion neutrons and X-rays, as well as energetic electrons and ion beams, can be produced by means of plasma focus devices. After its invention in the 16th century, the uh, 16 decades, they were intensively studied as a nuclear fusion devices and were described in detail among other references in the references between 3 up to 5. During the last decade, they began to be investigated as convenient sources for several technological applications, to be cited below of the mentioned radiations. Essentially, these devices are plasma accelerators gone, where the plasma is generated in a low pressure between 1 up to the 10 millibar atmosphere by a pulse. The powerful capacitives discharge between a pair of coaxial cylindrical electrodes. The Lorentz force derives a plasma sheath along the electrodes, which radially collapses at the symmetry axis, forming a Hodgkin's plasma pinch of about 100 nanoseconds. Intense pulses of the electromagnetic radiation, as well as ions and electrons beams, are emitted as a result of the focusing processes. The electromagnetic emission from the collapsing plasma has a very high brightness and exhibits a broadband spectrum ranging from visible light to soft X-rays. Fusion reactions can be obtained if deuterium or deuterium-tritium mixtures are used, with the consequent emission of fast neutrons, the kinetic energy of the emitted neutrons being 2.45 megaelectron-volts in the first case and 2.45 megaelectron-volt or 14.1 megaelectron-volt in the second one. Both emissions are almost monochromatic, and the references that mentioned this phenomena is between the reference 3 up to the reference 5. Since a neutron and also the hard X-ray bears the duration of this source in the 10 up to the 100 nanosecond range, and that is its emission can be turned off, the plasma focus becomes an interesting alternative to commercially available radioisotopic sources of both neutrons and hard X-rays. Due to the high effective cross-sections of hydrogen for neutron dispersion, plasma-focused neutron pulses can be used as radiation probes to detect hydrogenated substances by means of neutron scattering. Examples of potential application of this radiation are soil humidity studies and detection of hidden dangerous or illegal substances, including drugs, weapons, and plastic explosives. The plasma-focused neutron emission is also suitable for dark matter research, radioisotopic production, and neutron therapy. Other reported applications are radiographies of biological samples, small pieces made of different materials, and a rotating car wheel. In introspective image of small metallic pieces, even though several millimeter thick metallic walls were also produced. Additionally, a radiography of an aluminum turbine rotating at 6,120 rounds per minute using a plasma focused pulse was reported. The tomographic reconstruction of both surface and volume of small metallic objects was investigated as another non-conventional imaging application of the hard X-ray emission of plasma-focused devices. The spatial resolution of the digitalized image has demonstrated to be suitable for three-dimensional tomographic reconstructions of an object with just 8 projections. Other capabilities of the plasma-focused emission include lithography with a nanometer resolution, medical radiation therapy applications, industrial non-destructive testing, as well as thin film depositions. Compact and portable plasma focus are being developed to work efficiently on the field at relative low costs when compared to nuclear reactors or linear accelerator-based sources. Moreover, the feasibility of combining neutron and X-ray scanning simultaneously in a single device is a unique advantage of plasma phoci. However, plasma phoci still presents several challenges that must be overcome in order to extend the uses of these devices as X-rays and neutron source for commercial and industrial applications. In order to be useful over the widest range of applications, a plasma-focused device should be able to operate at a discrete repetition rate in order to produce average neutron emission rates about 10 to the power of 7 up to 10 to the power of 10 neutrons per second, and intense penetrating X-ray beams. uh, for example, Lee and his colleagues presented a 16 Hz plasma focus operating in neon. More recently, Raposi and his colleagues developed a mobile repetitive device for industrial applications. In the current paper, a repetitive plasma focus device operating with deuterium aimed to a pulsed source of neutrons and hard X-rays is presented. The repetition rate is controlled by means of a variable clock synchronized with a triggering system and a power supply, which ensures a regular operating up to zero point 0.2 Hz. Moreover, the feasibility of technological applications are analyzed. Now I want to go through the device design and output characteristics. A 4.7 kJ small chamber matter-type plasma focus was used as repetitive radiation source. The gas chamber was filled with 4 millibar of an admixture of 2.5% in volume of argon in deuterium. The cylindrical chamber 1 cubic meter is made of a 3 millimeter thick stainless steel tube. The 2 millimeter thick front of the chamber is a stainless steel disc and 100 millimeter OD used as the hard X-ray emission window. The electrodes are concentric cylinders 85 millimeter length, 38 and 73 millimeter OD respectively, made of hollow electrolytic copper and 12 3 millimeter diameter brass rods respectively. The anode base is made of brass, a 50 millimeter OD cylindrical Pyrex insulator, 4 millimeter thick, 30 millimeter length is located covering the anode at the base. The chamber design is optimized for hard X-ray and fast neutron production. The footprint of whole device is 0.60 square meter, its height being is 1.3 meter. The capacitor bank is composed by three modules of six 0.7 microfarad Maxwell capacitors. The bank was charged using a 10 kilowatt Maxwell CCDS power supply. The modules were connected in parallel to the discharge chamber through three Maxwell spark gaps. Model is a 40,264, which were triggered simultaneously by means of a car ignition coil. The device was able to operate regularly at 30 kW at a repetition rate up to 0.2 Hz during runs of the 2 minutes, maintaining the temperature within reasonable range. The external temperature of the anode reached to the 30 degrees of Celsius above room temperature after each run. The continuous compressed air flow needed to set the spark gap operating voltage and cleaning was sufficient to cool these elements. The external surface of the spark gap plastic encasing body heated up only few degrees over the room temperature, whereas the chamber refrigerated by natural air convection with the environment. A microprocessor-based control system synchronized both the power supply and the triggering system based on the figure 1. The peak current delivered was in a very short, about 360 kiloampere. Higher frequencies are in principle possible to achieve introducing a cooling system of the chamber and electrodes. The higher frequency achieved during the test was 1 Hz during 20 seconds. Now we see the figure 1 illustrates operation scheme of the synchronized charging and triggering systems. There is a virtual Maxwell CCDS power supply, and there is a two-trans capacitor bank control system which go to the spark gap and car ignition coil trigger system, and the next and the left side is discharge chamber. The discharge current was monitored by a non-integrating Rogowski coil. The X-ray emission was detected with an E102 ampere scintillator optically coupled to a photo multiplier (PMT) polarized at 800 volts and placed 3.9 meters away from the chamber. The rogoscopic coil and the PMT or photomultiplier signals were acquired with a Tektronix TDS 540 ampere oscilloscope. Both the PMT or photomultiplier and the oscilloscope are placed inside a Faraday cage. Figure 2 shows the rogoscopic coil and a PMT or photomultiplier signals acquired during a 24-shot sequence at 0.2 Hz. It can be observed that both the amplitude and the first quarter of period of the rogoscopic coil signal are repetitive from shot to shot between positive-negative 50 kA per microsecond and positive-negative 50 nanosecond respectively. The pinch time occurs at 1.48 positive-negative 0.12 microsecond, close to the peak current time, which is 1.27 positive-negative, which is the tolerance at 0.05 microsecond. After integrating the Rogowski coil signal, it results the current at which is always above 90% of the maximum current value. As it usually happens, plasma-focused discharge focusing not always occur in every shot, specifically when working in rep rate mode without replacing the working gas. In the case shown in the figure 2, 4 shots out of the 24 failed to focus, whereas very intense current dips were attained in 16 of the others. The remaining 4 focalizations were not particularly intense. The PMT or photo multiplier signals show that X-ray pulses are produced around 35 nanoseconds after the pinch, lasting each about 50 nanosecond FWHM. The neutron yield was determined by silver activation. The detector consists of a 30 multiplied by 30 multiplied by 15 cubic centimeter rectangular box filled with the paraffin. You can see the figure 3 in which for Victorian 1B 85 gigahertz, each surrounded by a 300 micrometer thick silver foil and polarized to 800 volts are allocated. The gigahertz are placed respectively inside four holes 2 centimeter in diameter by 9 centimeter in depth drilled on the diagonals of one of the 30 multiplied by 30 square meter faces at 9 centimeter from the face center. The amount of paraffin allows for the necessary neutron thermalization to match the silver resonance peak for neutron capture. With a beta decay located at 5 electron volt, the background counts of this detector are 66 to positive negative 8 in a time interval of 20 seconds. And now there is two plots. The first plot is figure 2, Rogowski coil and photomultiplier signals acquired during a 24 shot sequences. You see that the x-axis we have a time based on the microseconds from the 0 up to the 3.5 microseconds, and the y-axis we have a photomultiplier based on the volt and Rogowski signal based on the kiloampere per microsecond. The next sections we have figure 3 illustrates a scheme of fast neutron detector. It is a 30 multiplied by 30 multiplied by 15 cubic meter centimeter paraffin block with four Victorian IB 85 gigahertz, each one surrounded by a 300 micrometer thick silver foil. Figure 4 shows the measured neutron yield per shot recorded during four independent runs lasting 3 to 5 minutes of 0.2 Hz operation. The average neutron yield is about 10 to the power of 8 neutrons per shot during the first 20 shots. After that, the yield gradually decreases until it reaches half that number around the shot 60. This may be in part due to a buildup of impurities in the filling gas along the run, which slows down the current sheets, resulting in a pitch time delay on a corresponding decrease of the pitch current, or due to the degradation of the focusing efficiency caused by such impurities. Each run was down with the same gas filling, but it was fully refreshed before starting the run. Figure 4 illustrates neutron yield for each shot during several runs between 3 and 5 minutes long. Applications, the methods and results. Both neutron and X-ray images of the plasma focus device were tested for different technological applications with a potential industrial or therapeutical use. The following section describes the obtained results. Perspection by fast neutron scattering. The neutron pulses emitted by a plasma focus can be used to determine the presence and, after the proper calibration, estimate the concentration of hydrogenated substances in the proximities of the device. The basic idea of the method is depicted in figure 5. A silver activation counter, like on the one described in section 1, is used as a reference detector to register the neutron yield in each part of the emitted neutrons are scattered by the target. If present, they are registered by a second detector. The second detector doesn't contain paraffin for it to be sensitive to scattered slow neutrons, and at the same time to be insensitive to the direct plasma focused neutron radiation. Moreover, it is shielded with borax on every side but one to filter slow neutron not coming through its window. Figure 6 shows a diagram of the detector. It is important to note that this is a side-on agonistic, that is, the source and detection system are on the same side respect to the substance to probe. Figure 5, you see, it's showing conceptual scheme for the detection of hydrogenated substances by neutron scattering. The scattered neutrons are monitored by directional detector, scatter neutron detector. The reference detector, which is like that shown in figure 3, is used to monitor the neutron yield per shot. You see that we have a H substance, and then a scatter neutron detector, discharge chamber, and reference detector. Now we are going to the Giger tube. Figure 6 illustrates the range of the scattered neutron detector. Dimensions are in millimeters. The feasibility of this kind of application using the present device was tested interrogating a wooden rack with 56 plastic bottles, 500 cubic centimeter each, placed close to the plasma focus chamber. For cases were analyzed: A. All the bottles empty, the B sections filled with the water, the C sections, this one 32 filled, and this one all of the filled. You see the figure 7 illustrates the four different configurations of empty and full filled bottles considered to the test systems for water amounts detection. From left to the right, there are 0, 16, 32, and 56 water filled bottles respectively. Figure 8 illustrates that a scatter and direct neutron counts for the different configurations of bottle shine. Figure 7, the number of the right of each linear feet refers to the number of field bottoms. In the x-axis, we have a reference detector counts, and the y-axis, we have a scattered neutrons detector. Figure 8 shows plots of slow neutron against fast neutron counts for different configurations with their respective linear fits. The slopes allows to discriminate between the different amount of the water located at few meters of the plasma focus chamber. The experimental values equilibrium resulted in 0.161, positive negative 0.011, and 0.207, positive negative 0.011. And another value is 0.2838, positive negative 0.0092, and another value is 0.348, positive negative 0.013 for cases 2 to D respectively. The experimental values were checked against as MCMP simulation of the experiment. The simulation included the bottles, the laboratory floor, ceiling, and walls, the capacitor bank, the wooden rack, and the Bose detectors. Figure 9 shows a scatter plot of the experimental values against those numerically simulated. An acceptable agreement between the Bose quantities is found. The dot dash line included in the plot represents complete agreement. E is equal to Bring the error bars in and correspond to the uncertainties in the material composition of the laboratory building. The next section is hard X-ray retrospective imaging of metallic pieces. Plasma focus operating in single shot made has demonstrated to be a hard X-ray source suitable to obtain retrospective images of small metallic objects. Commercial AGFA Gurix ortho-regular cassette film system was used together with a standard developer and fixer recommended for that film. No special procedures other than those indicated by the manufacturer were required to process the films. Figure 10 illustrates the imaging setup. The objects and the film are placed on the electron axis outside the stainless steel chamber about 1 meter away from the chamber front wall. Figure 9 shows scatter plot of the experimental slopes against their corresponding numerical simulations and the dot dash line corresponds to is equal to empty. Figure 11, Part A shows a digitalized radiograph of a metallic BNCT collector image with a single shot through a 9 mm thick iron flange. The dark circle near the upper left of the block is a two-hole made on the flange close to its border. For comparison, figure 11 part B shows the same piece radiographed without interposing the flange. To determine the spatial resolution of the radiographs, a 10 mm thick aluminum block screwed with two 1 per 4 20 balls made of the brass and steel respectively was radiographed. Figure 12 showed the radiograph was where some millimetric details of the thread can be easily distinguished 1.27 mm per 10. The overall spatial resolution is 1 per 60 mm 6 pixels of the scanned image per millimeter measured on the object. The degree of detail shown in figure 8 and 12 implies that the source size is well below the millimetric scale, since otherwise the image would not show sharp borders with such good contrast. Finally, the figure 13 snapshots of the strong box containing the BNCT and the brass boards are shown. A single shot radiograph of the set is shown in figure 14. So you see figure 10 illustrates imaging setup. The film is placed outside the discharge chamber on the electrode axis about 1 meter away from the chamber front wall. Discussion sections: a repetitive plasma-focused device capable of emitting fusion neutrons and hard X-ray was presented, showing that it can be operated at a moderate repetition rate for several minutes. The performance and thermal conditions of the device is stable during 2 up to 3 minutes runs. Higher shot frequencies can in principle be achieved if some thermal management is provided to cool the heat dissipated in every shot. It was demonstrated that the emitted neutrons can be used to detect the presence of water near the discharge chamber by neutron scattering. In principle, this procedure can be extended to detect other hydrogenated substances such as explosives or drugs. Radiographic images could be obtained from the hard-risk emissions showing submillimetric spatial resolutions with exposition time around 50 nanoseconds. The energy and intensity of the X-rays are sufficiently high for the inspection of metallic objects located behind or inside several millimeters of iron or steel. These characteristics are suitable to develop non-intrusive detection systems of internal defects and imaging of fast-rotating components. Figure 11 illustrates a digitized radiograph of a metallic BNCT connector image with a single plasma focus rod to a 9 mm thick iron flange. The dark circle near the upper left of the block is through hole made on the flange close to its border, and the part B the same connector image without interposing the flange. You see that there are this upper left, this circle and so-called dark circle near the upper left is a block through the hole made of the flange close its border. Here we have a bolt in figure 12, a 10 mm thick aluminum block with two 1 per 2 up to 20 bolts, one made of the steel left side and another from the brass made of the brass in the right side. Figure 13 illustrates a snapshot of a strong box containing DNCT and a brass bolt. Figure 14 illustrates radiography of the strong box shown in figure 13. So thank you so much for watching my tutorial video until the end. If there is any simulation which is related to this literature, you can download it from the github.com/masterscript or github.com/culturescript or /saffron Today is 26th of June 2026. Time is 6 o'clock in the morning.